A galaxy full of stars existed when the universe was just 2% of its current age. We have the image, we have the data, and scientists have no clean explanation for how it got there. The James Webb Space Telescope keeps finding galaxies that are too big, too old, and too heavy to exist according to everything we know. Galaxies with dead stars older than the universe itself. 70 hidden giants packed with metals that should have taken billions of years to forge. A glowing red dot that turned out to be a black hole eating so much gas it looked like an entire galaxy. Every answer pulls up a bigger question. If you enjoy what you find here, subscribe and leave a like. We are about to go back to the very edge of time. Let's begin. 13.8 billion years ago, everything that exists exploded into being from a single point smaller than a grain of sand. That is the birth certificate of the universe. Scientists have tested it, measured it, and defended it for decades. Every telescope, every calculation, every piece of data kept pointing back to the same number, 13.8 billion years. Case closed. Then James Webb launched, and the forgeries started showing up. One by one, galaxies appeared in Webb's images that had no business being there. Fully formed, massive, ancient, sitting in a period of cosmic history when, according to our best science, they could not yet exist. Each discovery was filed away as an anomaly. Then another appeared, then dozens more. Astronomers started asking a question they had never seriously entertained before. What if the birth certificate is wrong? To understand why these galaxies are so shocking, you need to understand what the universe looked like at the very beginning. Picture the densest, hottest soup you can imagine. Every particle that makes up everything you have ever touched, all packed together in a space smaller than a marble. Then it exploded outward, fast. The universe was born screaming. In those first few seconds, there were no atoms, no molecules, no structure of any kind. Just a blinding fog of energy and particles crashing into each other at incredible speeds. Space itself was stretching outward in every direction, pulling everything apart. After about 380,000 years, the universe cooled down just enough for the first hydrogen atoms to form. For the first time, matter existed. Simple matter, just hydrogen and a little helium, and then everything went dark. No stars, no galaxies, no light, just a vast, silent ocean of hydrogen gas, slowly drifting through an expanding universe. Scientists call this period the Cosmic Dark Ages, and it lasted for hundreds of millions of years. During that time, gravity was doing quiet, invisible work. It pulled hydrogen together in small clumps. Those clumps grew denser, denser, denser still, until the pressure at the center became so extreme that atoms fused together and released energy. The first star lit up. That moment, whenever it happened, was one of the most important events in the history of the universe. A single point of light in an ocean of darkness. Then more lights appeared. Stars gathered into clusters. Clusters became the earliest, messiest, smallest galaxies. It was a slow process. Gravity is patient. Building a galaxy from scratch, from nothing but gas and time, should take billions of years. That is what the models said. That is what every simulation confirmed. Small galaxies first, big galaxies later. A long, gradual process stretching across cosmic time. Webb looked back at that era and found something else entirely. The galaxies it spotted were massive, bright, structured. Some of them contained as many stars as our modern Milky Way, which took over 10 billion years to build. These early galaxies had only a few 100 million years. That is the difference between building a skyscraper and growing one overnight from a single seed. Scientists stared at the data. Some assumed instrument errors. Others proposed creative explanations. A few quietly admitted they had no idea what they were looking at. The universe had shown them its birth certificate, and somewhere in those early images, something had scrawled over the date. What Webb found next made the mass problem look simple. The Big Bang did not create a universe full of stuff. It created a universe full of chaos. Most people picture the Big Bang as an explosion in space, like a bomb going off in an empty room, debris flying outward, matter spreading across a dark backdrop. That image is wrong in almost every detail. Space itself did not exist before the Big Bang. The explosion was not in space. Space was the explosion. Every point in the universe expanded away from every other point simultaneously. There was no center, there was no edge. There was just heat, pressure, and energy stretching outward in all directions at once. In those first few minutes, the universe was so hot that even atoms could not survive. Protons and neutrons existed, but electrons moved too fast to be captured. Any atom that tried to form was ripped apart instantly. The universe was one enormous glowing plasma, opaque in every direction. Light could not travel more than a short distance before crashing into a free electron and scattering. For 380,000 years, the universe stayed that way, brilliant but blind, a fog so thick that no signal, no image, no information could pass through it. Then the temperature dropped below a critical threshold. In a relatively short window of cosmic time, electrons slowed down just enough to be captured by protons. Hydrogen atoms formed across the entire universe almost simultaneously. The fog cleared. For the first time since the Big Bang, light could travel freely through space in a straight line. That moment has a name. Scientists call it recombination, and the light released at that exact moment is still traveling through the universe today. We can detect it with radio telescopes as a faint glow coming equally from every direction in the sky. It is called the cosmic microwave background, and it is essentially a photograph of the universe at 380,000 years old. It is the oldest image of anything that exists. But after recombination, something unexpected happened. The universe went dark. Hydrogen atoms formed, yes, but hydrogen atoms on their own do not glow. They do not emit light. The plasma had stopped shining. The first stars had not yet ignited, and the universe entered a period of genuine, total darkness. No photon of visible light existed anywhere across billions of light years of space. Just cold hydrogen slowly drifting, slowly clumping under the pull of gravity. This era lasted somewhere between 150 million and 800 million years. The exact length is still debated. During that time, gravity quietly worked on the hydrogen. It gathered into filaments, like a vast, invisible web stretching across the cosmos. Where filaments crossed, matter piled up. Pockets of gas grew dense enough to collapse inward. Temperature at the center climbed. Pressure built. The Dark Ages ended the moment the first star ignited. That single event flooded the surrounding space with ultraviolet radiation and began burning away the hydrogen fog. More stars followed. The universe began to light up, slowly, like city lights appearing across a dark valley at dusk. Every galaxy you have ever seen in a photograph came from that process. Slow, patient, building over millions and billions of years. Or so scientists believed, because Webb is now showing us that some galaxies skipped most of that process entirely. How they did it is the mystery that is keeping astronomers awake at night. Gravity is the weakest force in the universe. You fight it every time you pick up a pencil. A tiny magnet on a refrigerator beats it without effort. And yet gravity built every star, every galaxy, and every structure in the cosmos from scratch. Given enough time, even the weakest force wins. After the cosmic dark ages began, the universe looked almost perfectly smooth. Hydrogen gas spread across space in every direction, with only the faintest variations in density. Some regions had slightly more gas. Some had slightly less. The difference was tiny, roughly 1 part in 100,000. If you shrank the entire universe to the size of a football field, the dense regions and the empty regions would differ in height by less than the thickness of a hair. But gravity noticed. Over millions of years, those tiny variations grew. The slightly denser regions pulled in neighboring gas. As gas piled up, the gravitational pull grew stronger. More gas arrived. The region grew denser still. This process has a name: gravitational collapse. And it is the engine behind every star that has ever existed. Deep inside one of these collapsing clouds of hydrogen, the pressure at the center reached extraordinary levels. The gas heated up. Hydrogen atoms moved faster and faster. Then, when the temperature hit about 18 million degrees Fahrenheit, something remarkable happened. Two hydrogen nuclei collided hard enough to fuse together. They merged into a heavier atom and released energy. That energy pushed outward against the weight of all the gas pressing inward. A star was born. The first stars were almost certainly nothing like our Sunday scientists believe. They were enormous by modern standards. Some potentially hundreds of times more massive than our Sunday. They burned ferociously hot and ran through their fuel in a fraction of the time. A star like our Sun will live for about 10 billion years. These early giants likely burned out in just a few million years. That short lifespan mattered enormously for what came next. When a massive star exhausts its fuel, it collapses under its own gravity and then explodes in a supernova. That explosion scatters the star's material across space. And inside massive stars, nuclear fusion had been building heavier and heavier elements throughout the star's life. Carbon, oxygen, silicon, iron, elements that hydrogen alone could never produce. So, the first stellar explosions seeded the surrounding gas with new materials. The second generation of stars formed from clouds that were now slightly richer in chemistry. Each new generation passed more complexity forward, more elements, more dust, more variety. Over millions of years, gravity gathered these enriched clouds into larger and larger structures. Clusters of stars formed. Then, those clusters merged. Then the merged clusters developed rotating disks of gas and dust around a dense central core. The first galaxies were small and chaotic by modern standards. Irregular shapes, violent star formation, no clean spiral arms. Scientists expected James Webb to see exactly these kinds of tiny, messy, dim collections of stars in the early universe. Webb saw something far more impressive instead. Galaxies that looked nothing like primitive beginners. Galaxies that looked like they had been building for billions of years longer than the universe had been alive. Something clearly accelerated the process. And the next discovery suggests that acceleration started even earlier than anyone imagined. For decades, the standard picture of galaxy formation was built on one simple idea. Big things come from small things, and small things take time. Cosmologists ran simulations on some of the most powerful computers ever built. They started the simulation at the Big Bang, fed in the known laws of physics, and let it run. The gas collapsed, stars formed, galaxies grew, and every major simulation produced the same result. In the first few 100 million years, the universe should have been populated by dwarf galaxies. Small, dim, irregular, containing maybe a few 100 million stars at most. Our own Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. According to the simulations, building something that size requires billions of years of mergers, collisions, and steady star formation. You start with small pieces. Those pieces crash into each other and merge. The merged object grows larger, more mergers follow. Over billions of years, a giant spiral galaxy slowly assembles itself like a cosmic jigsaw puzzle. This process is called hierarchical structure formation. It is one of the most tested ideas in all of cosmology. The simulations matched observations from older telescopes. The math worked, the timeline held together. So when astronomers designed the James Webb Space Telescope, they built it partly to observe this early era of small, fragile proto-galaxies. They expected to see cosmic babies, faint smudges of light, the raw ingredients of what would eventually become the massive galaxies we see nearby today. The telescope cost $10 billion and took over 20 years to build. It launched on Christmas Day, 2021. Scientists around the world held their breath as it unfolded its golden mirror in space. one panel at a time, over the course of 2 weeks. A single failure in that unfolding process would have destroyed the mission entirely. It worked perfectly, and within its first year of observations, it began returning images that made the theorists deeply uncomfortable. The early universe had galaxies that looked nothing like cosmic babies. They looked like fully grown adults, structured, massive, rich in stars, some of them sitting just 300 to 500 million years after the Big Bang, already containing stellar populations that rivaled modern large galaxies. One of the lead researchers on an early analysis described the situation bluntly. Finding galaxies this large, this early, was like discovering a fully built skyscraper at an archaeological dig site from the Stone Age. The tools to build it should not have existed yet. The simulations had not predicted this, the models had not allowed for it, and the data was too clean to dismiss. Scientists began hunting for explanations. Maybe the images were misleading. Maybe some of the light was from something other than stars. Maybe the distance measurements were off. Each possibility got tested. Each test came back confirming what Webb had seen. The galaxies were real. They were massive. And they were exactly as far away as the data said. The standard picture of slow, fragile galaxy formation had run into something it could not explain. And the strangest part was still hiding inside the galaxies themselves, in a layer of material that should not have been there at all. Building the James Webb Space Telescope took longer than most people spend in their entire careers. The project started in 1996. Engineers spent the next 25 years solving problems that had never been solved before. The telescope needed to see infrared light, which is essentially heat radiation. The challenge was that the telescope itself generates heat. If any warmth from the instrument reached the mirror or the sensors, it would drown out the incredibly faint signals coming from the edge of the universe. The solution was a sun shield the size of a tennis court. 5 layers of a special material, each as thin as a human hair, folded up for launch and designed to unfurl in space. One side of the shield faces the sun and reaches temperatures hot enough to melt lead. The other side, where the telescope operates, drops to around negative 370 degrees Fahrenheit. That is colder than the surface of Pluto. At that temperature, the telescope's own heat signature essentially disappears. The detectors can pick up signals so faint that they represent the heat of a single firefly seen from the distance between Washington and Tokyo. The mirror itself is made of 18 hexagonal segments, each coated in a microscopic layer of real gold. Gold reflects infrared light more efficiently than any other material. Each segment had to be polished to a smoothness measurable in nanometers, a billionth of a meter, across a mirror nearly 21 feet wide. Aligning all 18 segments to act as a single perfect surface required months of careful adjustment after launch. The telescope launched on Christmas Day in 2021 from a jungle launch site in South America. It rode a rocket into space, folded like an origami sculpture. Over the next 2 weeks, it unfolded itself in a sequence of 344 separate mechanical steps. Engineers had identified that sequence as the most complex spacecraft deployment in history. Every single step had to succeed. There was no repair mission possible. Webb sits at a point in space called the second Lagrange point, roughly 1 million miles from Earth. At that distance, the gravity of the Earth and Sun balance in a way that lets the telescope orbit without using much fuel. It stays in permanent shadow, always pointed away from the Sun and Earth simultaneously. In July 2022, Webb released its first scientific images. The response from the global scientific community was immediate. One image showed thousands of galaxies in a patch of sky smaller than a grain of sand held at arm's length. Many of those galaxies had never been seen before. Some appeared to be among the oldest objects ever observed, but even those early images were just the warm-up act. As Webb turned toward the deepest, most ancient corners of the cosmos, it started finding objects that did not fit the timeline. Objects that the standard model of cosmology had no room for. The further it looked, the more impossible the universe became. And Webb's secret weapon, the tool that made all of this possible, was something most people have never thought about: light itself. And what happens to it over 13 billion years of travel? Light is the only messenger the universe has ever sent us. Every piece of information we have about space, every galaxy catalogued, every star measured, every planet found, all of it arrived as light. And light, for all its speed, is subject to one unavoidable fact: it takes time to travel. When you look at the moon, you see it as it was about 1 second ago. When you look at the sun, you see it as it was 8 minutes ago. When you look at the nearest star beyond our solar system, you see it as it was 4 years ago. And when you look at a galaxy 13 billion light years away, you see it as it was 13 billion years ago. The universe is its own time machine. Every deep space image is a history lesson. But there is a complication. As the universe expands, it stretches the light traveling through it. Imagine drawing a wave on a rubber band, then stretching the rubber band. The wave gets longer. Light works the same way. As space itself expands, the wavelength of light traveling through it gets stretched out and longer. Short wavelengths are what our eyes see as blue or violet light. Long wavelengths appear as red. When light gets stretched beyond the red end of the visible spectrum, it becomes infrared. Our eyes cannot see it. Standard cameras cannot detect it. And most ground-based telescopes are blind to it. That stretching process is called redshift. The further away a galaxy is, the faster space between us, and it is expanding, and the more its light gets stretched. Galaxies from the very early universe have had their light stretched so dramatically that the ultraviolet radiation they originally emitted has been pushed all the way into the infrared range. To see those galaxies, you need an infrared telescope, a big one, in space. That is exactly what Webb is. Its detectors are tuned to wavelengths of light that are completely invisible to human eyes. When Webb looks at a galaxy 13 billion light-years away, it is collecting photons that left that galaxy when the universe was less than 1 billion years old. Those photons have been traveling ever since, stretching, cooling, arriving at Webb's gold mirror after a journey of almost incomprehensible length. Astronomers measure this stretching using a number called redshift. A redshift of 1 means the light has been stretched to double its original wavelength. A redshift of 10 means it has been stretched to 11 times its original wavelength. The galaxy MOME Z14, the most distant confirmed galaxy discovered so far, has a redshift of 14.44. Its light has been stretched to over 15 times its original wavelength. Getting a confirmed redshift measurement requires breaking the light into a spectrum, like a prism splitting sunlight into a rainbow. Each chemical element absorbs specific colors of light, leaving gaps in the spectrum. Those gaps act like a fingerprint. By measuring how far those gaps have shifted from their expected position, astronomers can calculate the exact distance to the galaxy. This technique is called spectroscopy. It transforms a blurry red smudge in an image into a precisely located point in cosmic history. And what Webb's spectroscopy kept revealing was that some of those red smudges had no right to be where they were. On the 11th of July, 2022, President Joe Biden stood in front of a screen at the White House and revealed the first full-color scientific image from the James Webb Space Telescope. The image showed a cluster of galaxies called SMACS 0723. In the foreground, large elliptical galaxies glowed with warm orange light, but the real shock was what surrounded them. Thousands of smaller, more distant galaxies filled every corner of the frame. Arcs of light bent around the foreground cluster, distorted by the mass of the galaxies acting like a cosmic magnifying glass. That distortion is called gravitational lensing, and astronomers use it to see objects that would otherwise be too faint to detect. The patch of sky covered by this image was about the size of a grain of sand held at arm's length, and inside that grain of sand, thousands of galaxies were visible, each one containing billions of stars. each one representing a different moment in cosmic history. Scientists who had spent their careers working toward this telescope described the moment of seeing the image as one of the most emotional experiences of their professional lives. One researcher said it felt like opening a door they had been pushing against for 20 years. But the emotional response faded quickly, replaced by something more unsettling. As teams began analyzing the galaxies in these early images, something kept coming up. Certain galaxies in the deep field looked older and more developed than they should have been given their distance. The working assumption was that strange measurements would resolve themselves with more data. Calibration issues, edge cases, outliers. That was the standard scientific response. Wait for more images, collect more spectra, see if the anomalies hold up. They held up. Over the following months, Webb turned toward different regions of the sky and found the same pattern repeating. Early galaxies that looked too evolved, too massive, too structured. Stars inside them that appeared to have been forming for longer than the timeline allowed. The deep field image had looked like a triumph, and it was. But buried inside it were the first hints that something fundamental about the standard model needed revisiting. Astronomers needed to know exactly how far away these troubling galaxies were, not approximately. Exactly. That required pointing Webb's spectrograph directly at the candidates and collecting their light for hours at a time to build up a detailed spectrum. What came back shook the field. Some of these galaxies sat at distances that placed them within the first 500 million years of cosmic history, and their properties, their masses, their stellar content, their chemical composition belonged to galaxies several billion years older. The celebration from the first image had barely finished when the questions started piling up, and the galaxy that would eventually break every previous distance record was already in the data, waiting to be found. In early 2026, a team of astronomers announced a discovery that reset the outer edge of the known universe. A galaxy, now called MOME Z14, had been identified at a redshift of 14.44. That number translates to a staggering distance. The light Webb captured from this galaxy left its source when the universe was only 280 million years old. 280 million years sounds like a long time. Set against the full 13.8 billion year age of the universe, it is roughly 2%. If the entire history of the universe were compressed into a single calendar year, MOME Z14 existed before the 4th day of January. The previous record holder was another galaxy discovered slightly earlier, sitting at a redshift of 14.18. Webb broke that record too, within the same period of observations. Records in early galaxy discovery are falling so quickly now that astronomers joke about updating their textbooks before they finish printing them. But the distance alone is not the shocking part. The shocking part is what this galaxy looks like. At 280 million years after the Big Bang, astronomers expected to find a faint, chaotic smear of light, a few young stars struggling to hold together, raw, unstructured, primitive. That was the prediction from decades of cosmological modeling. MOME Z14 showed up bright, structured, producing new stars at a rate that implied it had already been building itself for a significant amount of time before this snapshot was taken. A galaxy that should have been in its first moments of life looked like it had already graduated from something. The spectroscopic data confirmed the distance measurement beyond any reasonable doubt. The fingerprints of specific elements in the galaxy's light shifted precisely as expected for its distance, locked in the measurement. This was not a calibration error. The galaxy was exactly where the data said it was. And the team also noticed something in the light from MOME Z14 that hinted at a separate mystery entirely. The galaxy appeared to be clearing a bubble of neutral hydrogen gas around itself. That process, called reionization, was supposed to happen across the universe gradually over hundreds of millions of years. Finding a single galaxy powerful enough to do it locally, this early, implied a level of energy output that nobody had predicted for such a young object. One galaxy, 280 million years after the Big Bang, acting like it had been running at full power for much longer. Scientists flagged the finding as extraordinary. Some called it one of the most important observations in the history of the discipline. And MOME Z14 was standing on the shoulders of dozens of other anomalous galaxies Webb had already found, each one chipping away at the same assumption. Each one suggesting the universe had been far busier, far earlier than the models ever allowed. The next piece of evidence did not come from a single galaxy. It came from 70 of them at once. A single anomaly is a curiosity. 2 anomalies start a conversation. Dozens of anomalies demand an answer. When Webb returned its first images of unexpectedly large early galaxies, the scientific community responded cautiously. Outliers exist in every field of science. Data can be misread. Instruments can be miscalibrated. A single strange galaxy could be dismissed, studied, debated, and eventually explained away. But Webb kept looking, and the anomalies kept multiplying. Within its first year of full operations, researchers had identified a population of early galaxies that sat far outside the range of predictions. These were objects from the first 500 million years of cosmic history, and they were, on average, significantly more massive than the models said any galaxy in that era should be. One analysis, published by a team studying Webb's early deep field images, found roughly twice as many large galaxies in the early universe as cosmological simulations had predicted. Twice as many. And these were just the galaxies Webb could see clearly. Astronomers pointed out that the actual count was likely even higher, since some early galaxies would be obscured by dust clouds too thick for Webb to see through directly. The statistical weight of the finding changed the conversation entirely. A single outlier galaxy could be an instrument artifact. A handful could be explained by unusual formation conditions in a particular region of space. But dozens of massive, bright, well-developed galaxies scattered across different regions of the early universe pointed to something systematic, a process, a mechanism, something that the standard model of galaxy formation had simply never accounted for. Cosmologists use a standard set of equations to describe how galaxies should form. These equations were built on decades of observations and have passed every test thrown at them. When the observations consistently fall outside the range of predictions, one of 2 things is true. Either the observations are wrong, or the equations are incomplete. Webb's data had been checked and rechecked. The observations were solid, which meant the equations had a problem. Some researchers pushed back, arguing that the discrepancy was smaller than the alarm suggested. They pointed to uncertainties in mass measurements and redshift calculations. Valid concerns. Science runs on skepticism, but even the most conservative estimates still showed an excess. Even when researchers cut the numbers down by accounting for every possible measurement error, too many large galaxies remained. The finding also had a geographic quality to it. The excess galaxies were spread across the sky, popping up in independent observations from different research teams using different methods. That kind of consistency across separate studies is exactly what separates a systematic discovery from a fluke. The crisis was real, and for every researcher looking at galaxy counts, another team was focused on something even stranger inside those galaxies. The galaxies were full of things that had absolutely no business being there. Building a galaxy is the slowest construction project in the universe. The Milky Way, our home galaxy, contains somewhere between 200 billion and 400 billion stars. It has been assembling itself for most of the universe's 13.8 billion year history. Smaller galaxies crash into it. Gas streams in along cosmic filaments. Stars form, explode, and enrich the surrounding clouds. Generation after generation of stellar births and deaths, slowly adding mass and complexity over billions of years. That is the standard recipe, and according to every simulation ever run on the galaxy formation problem, you cannot skip steps. You cannot rush gravity. Building something the size of the Milky Way from a starting point of raw hydrogen gas requires time. Cosmologists calculated that minimum, it runs into the billions of years. Webb found galaxies that skipped the recipe entirely. Some of the galaxies Webb spotted in the first 500 million years of cosmic history carried stellar masses comparable to the modern Milky Way. That means they contained roughly the same number of stars, packed into a period of cosmic history when, by every model, they should have been assembling their very first generation of stars. Put it in human terms. Imagine a construction crew given the job of building a 100-story skyscraper. The materials arrive on day one. The foundation gets poured, framing begins. Based on the pace of all previous construction, the building takes 50 years to complete. Now imagine arriving on day 3 and finding the building already finished, fully furnished, with people living in it. That is the scale of the discrepancy Webb is revealing. The mass problem points to something specific. Either the early universe found a way to convert gas into stars far more efficiently than it does today, or there is some additional source of mass that astronomers are not accounting for. Both possibilities require rethinking assumptions that have been considered settled for a generation. The efficiency angle is compelling to many researchers. Today, when a cloud of gas collapses to form stars, only a small fraction of the available gas actually ends up in a star. The rest gets blown away by radiation pressure, stellar winds, and supernova explosions. It is an inefficient process, but in the early universe, conditions were different. The gas was denser. It was cooler in some regions. The magnetic fields and radiation environments were unlike anything in the modern cosmos. Some researchers believe that under those early conditions, star formation could have been far more efficient, more of the available gas converted into stars, faster, with less waste. Even that explanation, though, strains to cover the full gap. Some of the galaxies Webb found are so massive, so early, that even a dramatic boost in star formation efficiency barely begins to explain them. Something else may have been at work. Something that was hiding inside these galaxies, glowing so brightly it changed everything astronomers thought they were measuring. Not all of Webb's most important discoveries came from the brightest objects in the frame. Some came from things that were nearly impossible to see. In a major study, astronomers combined data from the James Webb Space Telescope with readings from the Atacama Large Millimeter Array, a cluster of radio telescope dishes spread across a high plateau in the Chilean desert. Together, these two instruments can detect objects that fall outside the range of either one alone. Webb sees infrared light. The Atacama Array detects longer wavelength signals produced by cold dust and molecular gas. When scientists pointed both instruments at the same regions of deep space, they found something that had been hiding in plain sight. 70 galaxies, all from within the first billion years after the Big Bang, all packed with thick clouds of cosmic dust. 70. At that distance, with that much dust, to understand why this is shocking, you need to understand what cosmic dust actually is. Unlike household dust, which is mostly dead skin cells and fabric fibers, cosmic dust is made of heavier elements: carbon, silicon, iron, oxygen. These are elements that only form inside stars through nuclear fusion and only escape into space when those stars explode as supernovae. Finding dust means finding evidence of dead stars. Specifically, enough dead stars to produce enormous quantities of this material. In a period of cosmic history when the very first stars should have been just forming, these 70 galaxies had already cycled through generations of stellar birth and death. The dust clouds were so thick that they blocked visible light entirely. That is why these galaxies were invisible to older telescopes and nearly invisible to Webb's optical instruments. They were hidden behind their own history. The only way to detect them was through the longer wavelength signals that pass through dust the way radio waves pass through walls. The sheer number of dusty galaxies was the headline finding. Astronomers had expected to find a handful, if any, in this era. Finding 70 suggested that dusty, chemically rich galaxies were common in the early universe. common enough to be a normal phase of early galaxy development rather than an exotic edge case, and their existence had layered implications. If early galaxies could accumulate this much dust, they had to have formed and exploded many stellar generations. The dust did not come from nowhere. Behind every grain of cosmic dust in those 70 galaxies was a star that had lived and died. And behind that star was another, and another. The universe, in its first billion years, was apparently a far more active, more violent, and more chemically complex place than the standard model ever suggested. But even the dust was just a symptom. The real question was about what had actually driven all that frantic star formation in the first place. And the answer, for at least some of these galaxies, may have been lurking at their very centers. Every rocky planet in the universe started as dust. Your bones contain atoms that were once cosmic dust. The screen you are looking at right now is built from elements that drifted through space as microscopic particles before gravity pulled them together. Dust is how the universe stores the raw materials of complexity. In the modern universe, dust forms in several ways. It condenses in the outer atmospheres of aging red giant stars, forming tiny grains of silicate minerals and carbon compounds. It also gets ejected into space during supernova explosions, when a massive star collapses and blasts its outer layers outward at millions of miles per hour. The explosion seeds the surrounding gas cloud with a spray of dust particles. Each one smaller than a human hair is wide. Over time, these grains accumulate in the clouds between stars. They cluster together in giant molecular clouds, the cold, dense regions where new stars eventually form. Dust plays a direct role in that process, helping gas cool down enough to collapse under gravity. So, dust is linked to dead stars. You cannot have significant quantities of cosmic dust without a significant number of stars that have already lived and died. That connection is a chain. No dead stars, no dust, no rocky planets, no chemistry capable of producing life. That chain has a minimum length. It takes time. Massive stars burn fast and die young, within a few million years. But even accounting for the fastest possible stellar life cycle, producing the quantities of dust seen in those 70 early galaxies requires multiple rounds of star formation. Wave after wave of stellar births, lives, and deaths, each one enriching the surrounding gas with more material. The dust in these galaxies implies a history that stretches back further than the galaxies themselves should allow. If a galaxy is only 500 million years old, and it is already full of second or third generation stellar material, then its first stars must have formed incredibly early and burned through their lives at extreme speed. Some scientists have suggested that the very first stars in the universe were so massive and so hot that they lived for only a few 100,000 years before exploding. If true, multiple generations of stellar death could have played out within the first few 100 million years after the Big Bang. That would explain the dust. But it requires stars of a size and energy that pushes the boundaries of what modern stellar physics considers possible. There is also the question of how dust survives at all. Supernova explosions do not just create dust, they also destroy it. The shock wave from an exploding star tears through surrounding space at incredible speeds, grinding dust grains back into individual atoms. For so much dust to exist, it either had to form faster than supernovae could destroy it, or it had to be protected somehow, perhaps deep inside thick molecular clouds where shock waves lose their energy before reaching the dust. Either scenario adds another layer of complexity to an already complicated picture. And beyond the dust itself, the material inside those grains pointed to something even more startling sitting inside these galaxies. When astronomers use the word metal, they do not mean iron or gold the way a jeweler would. In astronomy, any element heavier than helium counts as a metal. That includes carbon, oxygen, nitrogen, silicon, iron, everything on the periodic table that requires nuclear fusion to build. Hydrogen and helium came directly from the Big Bang, Everything else had to be forged inside a star. Finding metals in the early universe is, in a very real sense, finding the ashes of stars we will never be able to see. When Webb examined the light from those early massive galaxies and the team studying the 70 dusty objects analyzed their chemical signatures, they found metal abundances that were striking. These galaxies had oxygen, carbon, and other heavy elements at concentrations that implied sustained, intense stellar activity over a long period of time. The process works like this. A massive star is born inside a gas cloud made almost entirely of hydrogen and helium. That star spends its short life fusing those light elements into heavier ones in its core. Helium fuses into carbon, carbon fuses into oxygen, oxygen into silicon, silicon into iron. When iron builds up in the core, fusion stops generating energy and the core collapses. The resulting explosion scatters everything the star spent its life building into the surrounding space. The next generation of stars forms from gas that is now slightly enriched. It contains traces of all those heavier elements. Those stars, when they explode, add their own layer of enrichment, and so on. Each generation passes a richer chemical inheritance to the next. For the early galaxies, Webb found to contain the metal concentrations they show, they had to have gone through several of these generational cycles. Multiple rounds of massive stars forming, burning through their fuel, and exploding, all within a time window that, in cosmic terms, was extraordinarily short. One way to picture it is this. Imagine a factory that produces finished steel. To get steel, you need iron ore, coal, heat, and a long industrial process. Now imagine that factory opening for business and immediately producing finished steel on day one, with no record of ever mining ore or burning coal. The output exists. The history required to produce it does not. That is the puzzle. The metal abundance is present. Some researchers have proposed that the very first stars, called population 3 stars, were so massive and so short-lived that they enriched their surroundings in a single explosive burst that left almost no observational trace. These hypothetical giants, if they existed in the numbers required, could have seeded entire regions of the early universe, with heavy elements before the galaxy's Webb is seeing were even fully assembled. Population 3 stars have never been directly observed. They existed too early and too briefly to leave detectable light that survives to the present day. They are a scientific inference, a ghost population inferred entirely from the chemistry they left behind. Webb may eventually find evidence of them, and if it does, what it finds will almost certainly raise an entirely new set of questions. Science is built on baselines. A baseline is what you expect to find before you look. It is the prediction, the model, the number that every piece of new data gets compared against. The baseline for the first stars was clear. They should have ignited somewhere between 150 million and 400 million years after the Big Bang. That range had been calculated from the known physics of gravitational collapse, the density of the early hydrogen gas, and the rate at which the universe was expanding at the time. Webb started finding evidence that the baseline was off, significantly off. The chemical signatures inside early galaxies implied stellar generations that should have predated the earliest possible moment for star formation, according to the standard models. If the metals and dust in a galaxy 500 million years old required several cycles of stellar birth and death to produce, and each cycle takes at minimum a few million years, then the first stars in that galaxy had to have formed far earlier than the baseline allowed. This is one of the most disorienting findings in modern astrophysics. The evidence suggests that something was accelerating the collapse of the first gas clouds, something that the standard model does not include in its equations, at least not at the strength required. One candidate is dark matter. The universe is full of dark matter, an invisible substance that does not interact with light, but does interact gravitationally. Cosmologists believe dark matter forms a vast web of filaments and clumps throughout the universe, and that visible matter, gas and stars and galaxies, forms inside those dark matter structures. Early dark matter clumps could have acted as gravitational seeds, pulling gas together faster than models predicted and triggering star formation earlier than expected. Another candidate is primordial magnetic fields. If the early universe contained stronger magnetic fields than currently assumed, those fields could have influenced how gas clouds collapsed, potentially triggering faster star formation in certain regions. A third possibility, one that some physicists find deeply uncomfortable, is that the physics of the very early universe behaved differently than the physics we observe today. Some modified gravity theories predict that gravitational attraction was stronger in the early cosmos, which would have accelerated the collapse of gas clouds and compressed the entire timeline of first star formation. None of these explanations has yet gathered enough evidence to become a consensus. They remain competing proposals, each with supporting arguments and unresolved problems. What unites them is the shared conclusion: something happened in the first few 100 million years of the universe that the standard model does not fully explain. Something that built stars faster and more efficiently than theory allowed, leaving behind chemical fingerprints that Webb is now reading like a cold case detective reviewing old evidence. And those fingerprints were showing up in a very specific kind of object, an object that nobody expected to find in such numbers. An object so strange that the team that discovered it did not immediately know what they were looking at. When Webb's early images came back, one category of objects appeared again and again: small, compact, intensely red, showing up at extreme distances in multiple deep field images. Astronomers called them little red dots. They were too faint to analyze in detail at first, but their color was distinctive. In astronomical imaging, color carries information. An object that appears red in infrared observations at extreme distances has had its light stretched dramatically by the expansion of the universe. These objects were glowing with an intensity that implied enormous energy output for their apparent size. But what exactly was producing that energy was unclear. Initial guesses ranged across several possibilities. Some researchers proposed they were extreme starburst galaxies, regions of space undergoing a burst of star formation so intense that the combined light of billions of young stars created a single brilliant glow. Others suggested they might be galaxies with unusual dust structures that scattered light in a particular way. A few proposed they could be entirely new categories of astrophysical object. For months, they remained a genuine mystery. Webb's spectroscopic instruments were turned on them. The spectra came back strange. The signatures of highly ionized gas that had been stripped of electrons by intense radiation, were present in unusual quantities. That specific signature pointed toward one explanation above all others: active galactic nuclei. In plain terms, supermassive black holes at the centers of galaxies, actively feeding on surrounding gas. When a supermassive black hole feeds, material falling toward it forms a swirling disk of gas that heats to extreme temperatures. That disk, called an accretion disk, radiates with a brightness that can outshine the entire galaxy surrounding it. From billions of light years away, a feeding black hole can look like a single blazing star, or, in the case of these little red dots, like a compact, intensely red point of light. The implication was significant and, in some ways, both alarming and somewhat reassuring. If many of the little red dots were feeding supermassive black holes, then some of the galaxies Webb had flagged as impossibly massive were possibly not that massive after all. The extreme brightness attributed to an enormous stellar population might actually be coming mostly from a black hole. That was the relief. But the alarm followed immediately. Finding supermassive black holes, this numerous, this early, in the first few 100 million years after the Big Bang, was its own impossibility. Where did they come from? How did black holes this massive form in such a short time? The answer to those questions peeled back another layer of the problem, revealing something that made the galaxy mass issue look almost manageable. Every large galaxy in the modern universe has a supermassive black hole at its center, The one at the center of the Milky Way is called Sagittarius A. It contains the mass of about 4 million suns, compressed into a region of space smaller than the distance between our Sun and the nearest star. Astronomers observed a ring of stars orbiting it at high speed and measured its mass that way. It is genuinely enormous by human standards, but modest by the standards of the most extreme black holes known. Some galaxies host black holes billions of times more massive than our Sunday. The largest known black holes sit inside galaxies billions of light years away and contain enough mass to swallow tens of billions of stars. Building a black hole this massive takes time. The standard theory goes like this. A very massive star collapses at the end of its life, leaving behind a black hole with a mass of a few dozen suns. That black hole slowly eats surrounding gas and occasionally merges with other black holes. Over billions of years, it grows. The most massive black holes in the modern universe got that way because they had billions of years to feed and merge. Webb found supermassive black holes that were already enormous just a few 100 million years after the Big Bang. The timeline does not fit. A black hole that starts as a stellar remnant of a few dozen solar masses and grows by conventional means cannot reach billions of solar masses in only a few 100 million years. The math does not work out. Even feeding at the absolute maximum theoretical rate, conventional growth mechanisms fall far short. Scientists have proposed several routes around this problem. One involves primordial black holes that formed directly from the collapse of dense regions in the very early universe before any stars existed, and therefore skipped the stellar stage entirely. These primordial black holes would have started much more massive and had a head start on growing to extreme sizes. Another proposal involves the direct collapse of massive gas clouds into black holes without forming stars first. Under very specific conditions in the early universe, a cloud of gas might have been prevented from fragmenting into stars and instead collapsed directly into a single massive object, creating a black hole thousands of times heavier than a typical stellar remnant from the start. Both proposals are scientifically plausible. Neither has been directly confirmed yet. What is confirmed is that Webb has found multiple examples of galaxies in the first billion years of cosmic history, hosting black holes far larger than the standard model expected. And those black holes were feeding aggressively, so aggressively that their glowing accretion disks were outshining their host galaxies, creating the little red dots that confused astronomers for months. The feeding black holes explained some of the apparent mass crisis in early galaxies, but only some of it, because when astronomers stripped out the black hole light and looked at what remained, some of those galaxies shrank to expected sizes, and some stayed stubbornly, impossibly large. One of the most useful tools in science is knowing what to ignore. When astronomers first found the little red dots and realized many of them contained feeding supermassive black holes, it changed the way they looked at the entire population of early massive galaxies. If a black hole's accretion disk was contributing a significant fraction of the total light coming from a galaxy, then mass estimates based on that light would be wildly inflated. The galaxy would appear far more massive than it actually was. A team published a detailed analysis of this exact problem. They took a sample of early galaxies that had been flagged as impossibly massive and carefully modeled the contribution of the central black hole to each galaxy's total brightness. This required understanding the spectrum of light produced by an accretion disk, which has a different signature than the light produced by a population of stars, and mathematically separating the two. When they subtracted the black hole component, some of the galaxies shrank dramatically. Objects that had appeared to contain hundreds of billions of solar masses of stars turned out to contain far less once the black hole's light was removed. Their stellar masses fell back into a range that the standard model could accommodate. This was, for some researchers, a genuine relief. A portion of the mass anomaly had a clean explanation. Contaminated measurements, not a broken theory, but the analysis also produced something less comfortable. For a meaningful fraction of the galaxies in the sample, even after the black hole correction, the stellar mass remained too high. The galaxy was still more massive than it should have been for its age. The black hole was contributing some excess brightness, but the stars alone still outpaced what the models predicted. The correction helped. It closed part of the gap between observation and theory. Studies following this approach suggested it could account for some galaxies initially flagged as catastrophically anomalous. But approximately twice as many large early galaxies remained than the standard model predicted, even after applying these corrections across the full sample. The cleaning process also revealed something interesting about the black holes themselves. Some of the feeding black holes, when their host galaxies were stripped of the glare, appeared to be absurdly large relative to their host galaxy. In the modern universe, there is a rough relationship between the mass of a central black hole and the mass of the surrounding galaxy's bulge of stars. The black hole is typically a tiny fraction of the total. In some of these early galaxies, the black hole appeared to be a far larger proportion, suggesting that in the early universe, black holes grew faster than their host galaxies, rather than growing in lockstep. That finding suggested the relationship between black holes and galaxies was fundamentally different in the early universe than it is today, and it added another line to the growing list of things the standard model had not predicted. The remaining anomalous galaxies, the ones too massive even after subtracting the black hole light, sat at the center of a debate that was only getting louder, because hidden inside their stellar populations was a measurement that seemed to break something even more fundamental than galaxy formation theory. The black hole correction was a partial fix, a useful tool that closed part of the gap between what Webb found and what the models predicted. But partial fixes have edges, and at those edges, the real problem lives. After the corrections swept through the data, a stubborn population of galaxies remained. These were objects that had been carefully analyzed, had their black hole contributions measured and subtracted, and still came out too massive. Their stellar populations, the actual stars inside them, contained more mass than the universe had time to build. Researchers, who had hoped the black hole explanation would resolve the crisis, found themselves looking at a smaller but harder problem. The easy cases were gone. What remained were the galaxies that resisted every conventional explanation that had been applied so far. Some of these galaxies sat in the range of 500 to 700 million years after the Big Bang. Others were even earlier. All of them shared the same basic profile. Too many stars, too much mass, too little time to explain it. One of the clearest ways to understand the scale of the problem is to think about star formation rates. The models predict how many new stars a galaxy of a given mass should produce per year at a given point in cosmic history. Take the total stellar mass of one of these anomalous early galaxies and divide by the time available since the Big Bang. The star formation rate required to build that galaxy is, in many cases, 10 to 20 times higher than anything the standard model allows for. 10 to 20 times. That is not a rounding error. Researchers proposed modifications to the star formation efficiency argument, suggesting that the earliest galaxies converted gas into stars with far less waste than modern galaxies do. This is plausible in principle. The conditions were genuinely different. The gas was denser, the metallicity was lower, the radiation environment was unlike anything in the modern universe. But efficiency modifications alone, even generous ones, struggled to bridge the full gap for the most extreme cases. Some galaxies required a perfect storm of every favorable condition simultaneously, sustained over the entire available time window, just to be marginally possible. The community divided loosely into two camps. One group argued the anomalies, while real, were within the range of what the standard model could eventually accommodate with refinements. The other group argued the accumulation of evidence pointed to something genuinely new, a physical process, a modification to the underlying theory, or a missing ingredient in the cosmological recipe. Both groups agreed on one thing: more data was needed, and Webb kept providing it. Each new deep field observation added more galaxies to the anomalous list. The excess shrank slightly with each methodological improvement, then reappeared in the next dataset. It was a persistent signal, scattered across the sky, reproduced by independent teams using independent methods. And then a different team, looking at a completely separate set of galaxies, found a measurement that made the mass problem look almost secondary. They found stars that appeared to be older than the universe itself. Numbers in astronomy can be checked. That is the strength of the discipline. You measure a galaxy's distance using redshift. You confirm the redshift with spectroscopy. You estimate stellar age using the spectrum of light the stars emit. Multiple methods can be cross-checked against each other. Good science does not rely on a single measurement. So, when a team of researchers analyzed a set of galaxies at a redshift of 8, corresponding to a time when the universe was only about 600 million years old, and found that the stars inside those galaxies appeared to be between 900 million and 2.4 billion years old, the first response was to check everything. They checked the redshift. It held. They checked the stellar age estimates using 2 independent methods. Both returned similar results. The numbers pointed to a situation with no physical explanation. Stars inside a galaxy that existed 600 million years after the Big Bang were showing spectral signatures consistent with stars that had been forming for anywhere from 900 million to 2.4 billion years. In the most extreme cases, the implied formation date of those stars predated the Big Bang itself, stars older than the universe. The Big Bang is the starting point of everything. Time, space, matter, energy. All of it began at that moment. A star that began forming before the Big Bang is a logical impossibility. It requires a cause without a universe to exist in. Scientists did not conclude that the laws of physics had broken down. The more grounded response was to assume the measurement tools were encountering conditions they were not calibrated for. Stellar age estimation works by matching the light from a star to models of stellar evolution. Those models are built on observations of nearby stars and tested against well-understood clusters. But those models were developed for stars in the modern universe. Stars from the very early universe formed in a different chemical environment, from gas that contained almost no heavy elements, under conditions of temperature and pressure that have no modern equivalent. If the stellar evolution models break down at extreme distances and extreme ages, then the age estimates produced by applying them to early universe stars could be significantly wrong. The stars might appear older than they are because the models assume a chemical composition they do not actually have. This is the most scientifically comfortable explanation. The measurement technique has a known limitation when pushed to its outer boundaries. But comfortable does not mean confirmed. The alternate possibility that some aspect of the universe's history before the commonly accepted Big Bang left an imprint on the first stars remains an open question in a small but serious fraction of the cosmological community. What is certain is that the measurement exists. It has been made by a credible team using standard methods, and it has not yet been fully resolved. It sits on the growing pile of data points that Webb has produced, each one demanding an explanation, each one pointing in the same general direction. The theory that was supposed to explain all of this was under serious pressure, and it had a longer history of survival than most people realized. Figuring out how old a star is sounds straightforward. Stars change over time in predictable ways. They burn through hydrogen, swell into red giants, and eventually collapse or explode depending on their mass. By looking at where a star sits in that life cycle, you can estimate its age, but that process only works cleanly when you can see individual stars. At extreme distances, you cannot. When Webb looks at a galaxy 13 billion light-years away, it sees the combined light of billions of stars blended together into a single signal. Separating the contribution of old stars from young stars inside that blended light requires modeling. The models used for this job are called stellar population synthesis models. They work by simulating a mix of stars at different ages and masses, calculating the light each one produces, and adding it all together to create a predicted spectrum. Astronomers then compare that predicted spectrum to the observed one and find the best match. The best matching model gives an estimate of the galaxy's stellar age distribution. These models are impressively powerful, but they carry assumptions baked into every calculation. One major assumption is the initial mass function. This describes the ratio of massive stars to small stars that form in any given episode of star formation. In the modern universe, this ratio follows a consistent pattern across many environments. But in the early universe, where the gas had almost no heavy elements and the conditions were fundamentally different, the ratio may have been weighted far more heavily toward massive stars. More massive stars live shorter lives and die more violently. A galaxy with an unusual initial mass function would emit light that looks different from what the standard models predict, and could be misidentified as either older or younger than it actually is. Another assumption involves the contribution of evolved stars called thermally pulsing asymptotic giant branch stars. These are old, luminous stars in a late stage of life that emit a lot of infrared light. They can dominate the stellar population models in certain age ranges, specifically between about 1 and 3 billion years old. If early galaxies have more or fewer of these stars than expected, the age estimate shifts. A third source of error comes from dust extinction. Dust inside a galaxy absorbs blue light more than red light, making a galaxy's stars appear redder and therefore older than they are. The amount of dust in early galaxies is now known to be surprisingly high, thanks in part to the 70 dusty galaxies discovered in the combined Webb and Atacama observation. If dust corrections are underestimated in these analyses, the age estimates skew older. None of these error sources means the measurements are worthless. They mean the measurements carry uncertainty, larger uncertainty than the headlines sometimes acknowledge. The scientifically honest answer to the question of whether those early galaxies contain stars older than the universe is this: the data is real, the uncertainty is significant, and the full explanation has not yet been found. That combination of confirmed strangeness and unresolved uncertainty runs through almost every major discovery Webb has made, and it all traces back to a theory that has been under pressure longer than most people outside cosmology realize. The standard model of cosmology has a formal name. Scientists call it lambda cold dark matter, or lambda CDM. The lambda refers to a mathematical term representing the energy of empty space, what physicists call the cosmological constant. Cold dark matter refers to the type of dark matter the model assumes fills the universe. Together, these two components explain most of what we observe in the cosmos. Lambda CDM was built up over decades through careful testing. It correctly predicted the pattern of the cosmic microwave background, the faint afterglow of the Big Bang that fills the whole sky. It predicted how large galaxy clusters would form and how they would be distributed across the universe. It predicted the rate at which the universe was expanding. It predicted how much hydrogen and helium were produced in the first few minutes after the Big Bang. Every one of these predictions was confirmed by observation, not one at a time, but over and over by independent teams using different instruments and methods. That track record is why cosmologists defended lambda CDM so strongly when early anomalies appeared. A theory with this many confirmed predictions does not get replaced because of a handful of outlier galaxies. The bar for overturning it is genuinely high. The model also makes specific predictions about structure formation, about how dark matter forms the skeleton of the universe, the vast cosmic web of filaments and voids, and how visible matter, gas and stars, clusters inside that skeleton. These predictions have been tested by mapping the three-dimensional distribution of millions of galaxies. The results match the model's predictions with impressive precision. So when Webb started returning images of anomalous early galaxies, the first instinct of many cosmologists was reasonable skepticism. The history of science is full of initial anomalies that dissolved when the measurements were improved. Instrument calibration errors, biased samples, incomplete corrections. All of these can produce apparent violations of a well-tested model. Many of the early reports of impossibly massive galaxies did shrink when the analysis was refined. Some of the early mass estimates were revised downward once black hole contributions were properly accounted for. The model showed resilience, but the anomalies did not disappear entirely. The excess of large galaxies in the early universe persisted across independent studies. The unusual chemical signatures remained. The unexplained age measurements sat unresolved. Lambda CDM had absorbed challenges before and survived, but each previous challenge came from a narrower dataset. Webb was producing a broad, systematic pattern of anomalies across multiple independent observations, multiple object types, and multiple measurement techniques. The model's defenders were not wrong to require strong evidence before revising it, but the evidence kept accumulating. And somewhere in the history of the discipline, there was already a precedent for exactly this kind of slow, uncomfortable reckoning between a trusted theory and data that would not behave. That reckoning had happened before, and the people who triggered it had been ignored for years before the field finally caught up. Webb did not discover the tension between early galaxies and the standard model from scratch. It inherited a problem that had been quietly growing for over a decade. The Hubble Space Telescope, Webb's predecessor, had already found galaxies in the early universe that looked uncomfortably large. The results from Hubble's deepest survey images, collected over years of pointed observations, showed a higher number of massive early galaxies than models predicted. But Hubble's capabilities had a ceiling. It could not see far enough into the infrared to confirm the distances or properties of the most extreme early objects. The anomalies were flagged, debated, and ultimately set aside pending better instruments. In parallel, ground-based telescopes and surveys were mapping the distribution of galaxies across the universe and finding a different kind of crack. The Hubble tension, as it became known, emerged from the disagreement between two independent methods for measuring the rate at which the universe is expanding. One method used the cosmic microwave background, the other used a chain of distance measurements, built on a type of exploding star called a Type 1a supernova. Both methods should produce the same answer. They do not. The discrepancy between them has grown with each improved measurement, and now sits outside the range of what normal measurement uncertainty can explain. Something in the standard model's account of how the universe expanded may be missing. A separate anomaly appeared in surveys of the large-scale structure of the universe. The way galaxies cluster together on the largest scales showed small but persistent deviations from the predictions of Lambda CDM. The deviations were within the model's uncertainty range, but they kept pointing in the same direction across multiple independent surveys. Scientists labeled this tension sigma 8, referring to the specific parameter in the model that governs the strength of cosmic structure formation. None of these pre-Webb anomalies were individually strong enough to overturn the standard model, but together they formed a pattern. The model worked brilliantly in most regimes. It struggled in specific corners: the cosmic expansion rate, the growth of structure, the properties of the earliest galaxies. Webb was designed partly to address the galaxy problem directly. The expectation, or perhaps the hope, was that Webb's superior sensitivity would reveal that the anomalous Hubble-era galaxies were measurement artifacts. That better data would bring observations back into alignment with theory. Instead, Webb found more anomalies, deeper ones, in greater numbers, across a wider range of cosmic history. The cracks that had appeared years before Webb launched did not close when the new data arrived. They widened, and each crack pointed toward the same set of unknowns buried inside the standard model. One of those unknowns had been a placeholder in the equations for decades. Something everyone agreed was there. Something nobody could see. Everything you have ever seen is made of ordinary matter. Protons, neutrons, electrons, atoms, molecules. All of it interacts with light. It emits light, absorbs it, reflects it. That is how we see it. Ordinary matter makes up about 5% of the total energy content of the universe. The rest is mostly dark energy, which drives the accelerating expansion of the universe, makes up roughly 68%. Dark matter makes up about 27%. Neither interacts with light in any way we can directly detect. Dark matter has no glow, no reflection, no shadow. We know it exists only because of its gravitational effects on ordinary matter. Galaxy rotation curves revealed it first. Stars at the outer edges of galaxies orbit too fast. If galaxies contained only the visible matter we can see, the gravity of that matter would be too weak to keep those outer stars in orbit. They would fly off into space. They do not. Something is holding them in. Something invisible and massive, distributed in a halo around the visible galaxy. Dark matter forms the skeleton of the cosmos. The vast cosmic web of filaments that connects galaxy clusters across billions of light years is, at its core, a dark matter web. Visible galaxies form inside the dense knots of that web, where dark matter gravity pulls ordinary gas together. In standard lambda CDM, dark matter clumps together in a predictable way as the universe expands. Small clumps form first, then merge into larger ones over time. This process, called hierarchical clustering, sets the pace of galaxy formation. Galaxies can only form as fast as their surrounding dark matter halos grow, and dark matter halos, according to the model, grow at a specific rate tied to the expansion of the universe. If dark matter clumped faster in the early universe than the model predicts, the first dark matter halos would have been denser and more massive than expected. That would have given early galaxies deeper gravitational wells to form inside, allowing them to gather gas and build stars much faster than the standard timeline suggests. Several groups of researchers have published modified versions of lambda CDM in which dark matter behaves slightly differently in the early universe. Some proposals involve dark matter particles that have small but non-zero interactions with each other or with ordinary matter, causing them to cluster more efficiently under certain early universe conditions. Others involve changes to the nature of dark matter itself, proposing that it existed in a different state in the very early universe before transitioning to its current behavior. These are speculative modifications. They are mathematically developed and internally consistent, but they lack direct evidence. What they have in their favor is that they can be tuned to reduce the tension between the predicted and observed number of massive early galaxies. They represent the more conservative end of the debate, the possibility that the standard model needs a patch, not a replacement. But some of the evidence Webb has returned does not respond to patches. Some of it points towards something more fundamental, and the most uncomfortable evidence of all is sitting inside a question about the universe's deepest unknown ingredient. Efficiency sounds like a dry, technical word. In the context of galaxy formation, it describes one of the most violent processes in the universe. When a cloud of gas collapses to form stars, only a fraction of the available gas actually ends up inside a star. The rest gets blown away. Young, massive stars emit intense ultraviolet radiation that heats surrounding gas and pushes it outward. Stellar winds carry material away from star-forming regions at high speeds. And when massive stars eventually explode as supernovae, the shockwaves sweep through the cloud and scatter the remaining gas across light years of space. In modern galaxies, the star formation efficiency in any given cloud is typically around 1 to 3%. Out of a cloud of gas containing 100 units of mass, only 1 to 3 units end up in stars. The rest is expelled. It is a remarkably wasteful process by any measure. Now consider what the early universe looked like. The first galaxies formed inside dark matter halos, where gas was collapsing rapidly under strong gravitational pull. The gas had almost no heavy elements, which means it cooled less efficiently in some ways but lacked the dust and molecular compounds that tend to fragment modern clouds into smaller, lower-mass stars. Without that fragmentation, gas clouds could collapse more directly into massive, fast-burning stars. Higher-mass stars form faster. They burn through their fuel quicker. They produce more ionizing radiation per unit of mass. In a very early galaxy, A single burst of massive star formation could have triggered a cascade of secondary star formation in surrounding gas, compressing neighboring clouds and igniting new stars in rapid succession. Some researchers have modeled this feedback process and found that in the right conditions, star formation efficiency in early galaxies could have been dramatically higher than today, perhaps 10%. In some extreme models, even higher, at 10% efficiency. The rate at which early galaxies built stellar mass jumps by a factor of 3 to 10 compared to modern star formation. That alone could account for a significant portion of the excess mass Webb is observing. A galaxy that seems to have grown impossibly fast starts to look more plausible if each episode of star formation was converting gas into stars 10 times more effectively. The problem is the feedback. The same intense radiation and supernova activity that drives high-efficiency star formation also tends to blow galaxies apart. Small early galaxies had shallow gravitational wells. A burst of supernovae intense enough to explain the observed stellar masses might also have been energetic enough to blast the galaxy's gas reservoir into surrounding space and shut down further star formation. Balancing the efficiency gain against the destructive feedback is a delicate calculation, and the models do not yet agree on where that balance sits. Some analyses suggest the efficiency argument partially closes the gap. Others find it insufficient for the most extreme cases. The debate is active, and there is another layer to the problem that efficiency alone cannot touch, because some of the light Webb captured from the early universe was being blocked, hidden behind a fog that the very galaxies themselves were burning away. After the first stars lit up, the universe entered a battle. Light on one side, fog on the other. The cosmic dark ages had left the universe filled with a diffuse sea of neutral hydrogen gas. Neutral hydrogen has a specific behavior. It absorbs ultraviolet light extremely efficiently. Any ultraviolet photon traveling through neutral hydrogen gets absorbed within a short distance. This turns the neutral hydrogen into a fog, opaque to certain wavelengths of light and capable of hiding objects behind it. The process of clearing this fog is called re-ionization. Energetic ultraviolet radiation from the first stars and galaxies poured into the surrounding hydrogen. That radiation stripped electrons away from hydrogen atoms, turning them from neutral atoms into ionized plasma. Ionized hydrogen is transparent. Once ionized, the fog clears and light can travel freely. The standard model predicted that reionization was a gradual process. The first galaxies produced ultraviolet radiation, but they were small and scattered. Slowly, over hundreds of millions of years, each galaxy carved out a small bubble of ionized hydrogen around itself. Those bubbles gradually grew and eventually merged. By about 1 billion years after the Big Bang, the process was largely complete. The universe became transparent. This timeline was well established. Observations from older telescopes had confirmed the broad outline. Reionization was a community effort, completed gradually by many small sources working in concert. Webb found something that did not fit this picture. The galaxy Mome, Z14, sitting at just 280 million years after the Big Bang, showed spectral signatures suggesting it was already clearing a significant bubble of neutral hydrogen around itself. At that epoch, the universe should have been almost completely neutral. The Great Reionization project should barely have started. For a single galaxy to be producing enough ionizing radiation to carve out a visible bubble of cleared hydrogen at that stage, it would need to be generating ultraviolet light at a rate that seemed improbable for such an early and presumably small object. The energy output implied by the bubble size exceeded what the standard model predicted for early galaxies of that type. Earlier reionization was also hinted at by other Webb observations. Some galaxies from the first 500 million years appeared to be seen through less neutral hydrogen than expected. The fog was thinner than predicted, suggesting that the reionization process started earlier and moved faster than the timeline allowed. If the first galaxies were more luminous, more energetic, and more efficient at producing ionizing radiation than the models assumed, reionization could have begun hundreds of millions of years earlier. The fog would have started clearing ahead of schedule. Galaxies that should have been hidden would have been visible. The whole history of how light reclaimed the universe would shift. This finding tied back to the mass problem and the efficiency problem and the dust problem, all pointing the same direction. The early universe was more active than anyone expected. The question was starting to become not whether the standard model needed revision, but how deep that revision needed to go. Reionization is not just a technical milestone in the history of the universe. It is the moment the universe became visible. Before reionization, the cosmos was functionally opaque to most forms of light. Ultraviolet photons, the most energetic form of visible radiation, were absorbed within short distances by neutral hydrogen. A photon emitted by a star in an early galaxy might travel only a short way before being captured by a hydrogen atom. Information could not cross the universe freely. Structure existed, but it was hidden. The completion of reionization changed everything. For the first time since the cosmic microwave background was released at 380,000 years after the Big Bang, light could travel freely across the full scale of the cosmos. The universe became readable. The timing of reionization therefore defines when the universe became an open book. Scientists had established the completion of reionization at roughly 1 billion years after the Big Bang through observations of distant quasars. Quasars are extremely luminous, feeding black holes, similar to the little red dots Webb found, but from a later era. When astronomers studied the spectra of quasars at different distances, they found that quasars from beyond a certain distance had their light significantly absorbed by neutral hydrogen, while closer quasars did not. That transition point marked where reionization had finished. Those observations placed the end of reionization fairly firmly. The start was less certain. Models suggested it began somewhere between 400 million and 600 million years after the Big Bang, when the first galaxies became numerous and bright enough to start ionizing their surroundings. MOME Z14 operates at 280 million years after the Big Bang. Reionization should not have been significantly underway yet. The galaxy should have been surrounded by dense neutral hydrogen on all sides. Instead, its spectrum showed a particular emission line, called the Lyman alpha line, that hydrogen gas emits when ionized. Detecting this line from a galaxy this early means the light carrying it was able to escape the galaxy and travel to us without being absorbed by surrounding neutral hydrogen. For that to happen, the neutral hydrogen around the galaxy had to already be significantly cleared. A cleared region at 280 million years means the reionization process started earlier than the models allowed. Much earlier. For that to happen, either MOME Z14 is an extraordinary outlier, a galaxy of unusual power sitting in an unusually favorable region of space, or the early universe had more sources of ionizing radiation, active earlier than the standard timeline includes. If the second possibility is correct, it means the entire history of reionization needs to be pushed back. Earlier start, faster progress, different topology of how the ionized bubbles spread. The textbook account of how the universe became transparent gets rewritten. That is a significant revision to a well-tested story, and it would require the early universe to have contained a population of energetic sources that the standard model simply did not include. Galaxies, possibly. Black holes, possibly. Or something else entirely. Science is comfortable with gaps. A gap in the data is an invitation. It means there is something left to find, something left to measure, something waiting to be understood. Gaps are part of the job. What is harder to be comfortable with is the possibility that something happened and left almost no trace. An episode in the universe's history that influenced everything that came after it, but whose direct evidence has been erased or hidden beyond the reach of current instruments. That possibility is being taken seriously by a growing number of cosmologists. The Standard Model begins its story at a fraction of a second after the Big Bang, during a period called inflation. Inflation is the proposed period of exponential expansion that took the universe from a microscopic speck to something roughly the size of a grapefruit in an almost incomprehensibly short time. Inflation solves several otherwise unexplained features of the cosmic microwave background. It remains the leading theory for the very earliest moments of the universe. But inflation is not directly confirmed. Physicists have proposed dozens of different versions of it, and distinguishing between them requires measurements that current instruments cannot yet make. The period before the cosmic microwave background is effectively inaccessible to observation. Light from before recombination cannot reach us because the universe was opaque. Some theories propose that the universe underwent a phase transition in its very early moments, similar to water freezing into ice. The properties of space itself changed. If such a transition occurred, it could have left behind density fluctuations, primordial black holes, or other structures that provided seeds for galaxy formation far ahead of the standard schedule. Other proposals involve a period of enhanced energy output from some early population of objects that has since faded entirely. Hypothetical objects like cosmic strings, topological defects in the fabric of space left over from a phase transition, could have seeded density fluctuations that allowed faster structure formation. They would have disappeared billions of years ago, leaving the anomalous galaxies as their only fingerprint. More recently, some physicists have explored the possibility that dark energy, the force driving the accelerating expansion of the universe today, behaved differently in the very early cosmos. A higher density of dark energy in certain early regions could have influenced how quickly matter collapsed into the first structures. Each of these ideas has the same feature. It proposes an early universe event that no telescope has yet been able to directly observe, but whose consequences are visible in the galaxies Webb is finding. The honest scientific assessment is that these proposals are speculative. They are mathematically developed and internally consistent, but they are not confirmed. They represent the outer edge of what the evidence suggests, explored by researchers willing to consider that the universe may have had a chapter we have not yet learned to read. Webb may not be able to read that chapter directly, but it is building the case that the chapter exists. The anomalies Webb has found did not produce a single new theory. They produced several, and the competition between them is ongoing, with new papers, new data, and new arguments appearing constantly. The most conservative camp holds that the Standard Model is essentially correct and that the apparent discrepancies will shrink as measurement techniques improve. They point to the real progress already made in the black hole correction work, the revised mass estimates, and the improved understanding of dust contributions to galaxy brightness. Each methodological improvement has brought some anomalous galaxies back within the model's predictions. Given enough time, this group argues, the full dataset will come into alignment. The second camp accepts that the Standard Model is basically right but needs targeted modifications. The most popular version of this position focuses on dark matter. Several research groups have proposed that dark matter in the early universe was more interactive or more clustered than lambda CDM assumes. Modifications to the nature of dark matter, such as giving it a small but non-zero self-interaction, or changing how it responded to the radiation field of the early cosmos, can produce denser, early dark matter halos and faster galaxy formation without requiring a full revision of the cosmological framework. The third camp argues for substantial modifications to the star formation physics inside early galaxies. Even within an unchanged cosmological framework, if early galaxies converted gas into stars with far higher efficiency and did so across a wider population than models assumed, the stellar masses Webb observes become more plausible. This position emphasizes that the physics of star formation is genuinely uncertain in early universe conditions. The fourth camp, smaller but vocal, argues that the combined weight of anomalies, the excess massive galaxies, the early reionization signals, the unexplained stellar age measurements, the Hubble tension, and the sigma-8 discrepancy points toward a more fundamental revision. They argue that lambda CDM needs a structural change, not just a patch. Proposals in this camp include modified gravity theories, changes to the properties of dark energy across cosmic time, and alternative cosmological models that differ from lambda CDM in their treatment of the very early universe. The fifth camp, the smallest and most speculative, is willing to entertain the possibility that some observational anomalies point toward physics genuinely beyond the standard model of particle physics, as well as beyond lambda CDM. These researchers explore ideas like primordial black holes formed before the first stars, new types of dark matter with unusual properties, and interactions between dark matter and dark energy that current theories do not include. What all five camps share is this: every group is paying close attention to Webb. The data it returns has already forced revisions to multiple preliminary conclusions. Each new deep field observation, each new spectroscopic confirmation, each new analysis of stellar populations in distant galaxies adds to the dataset that will eventually distinguish between these competing ideas. The debate is alive, and the implications of each possible outcome are enormous. Replacing a scientific theory is not like swapping one answer for another. A theory like lambda CDM is not just a single idea. It is a framework, a system of equations, assumptions, and interconnected predictions that spans everything from the behavior of the universe in its first second to the distribution of galaxies across billions of light years today. Every piece of that framework has been tested. Every piece connects to every other piece. You cannot pull one thread without checking how it affects the rest of the fabric. This is why scientists do not rush to replace a working theory even when anomalies appear. A replacement must do everything the original did, pass all the same tests, and also explain the new observations that broke the original. That is a high bar. History offers guidance on what this process looks like. Newtonian gravity held for over 200 years. It explained the orbits of planets, the tides, the trajectory of falling objects. When anomalies appeared, specifically the unexpected precession of Mercury's orbit and the bending of starlight around the Sun, the community did not immediately discard Newton. The anomalies were studied, debated, and eventually traced to a limitation of the theory at extremes of gravity and speed. Einstein's general relativity replaced Newton, and did so by absorbing everything Newton correctly predicted, while extending the framework to cover what Newton could not. A similar process may be underway now. The most mathematically developed alternatives to lambda CDM currently being explored include models where dark energy changes in strength over time, rather than remaining constant as lambda CDM assumes. Observations of distant supernovae and galaxy clusters are actively testing this idea. Preliminary data from surveys conducted in the years leading up to this analysis has shown hints of time-varying dark energy, though the evidence is not yet definitive. Other alternatives explore modifications to general relativity itself on cosmological scales. Some of these modified gravity theories predict a different rate of structure growth than lambda CDM, which could explain both the sigma-8 tension and the excess of massive early galaxies. A more radical option, explored by a minority of researchers, involves abandoning the assumption that the universe is the same in all directions on the largest scales. Lambda CDM assumes the universe is homogeneous and isotropic, meaning it looks the same regardless of which direction you face. Some researchers argue that the distribution of large-scale structures in the universe shows subtle anisotropies that could indicate this assumption is imperfect. A universe with large-scale structure, on scales bigger than current surveys have fully mapped, could behave differently than lambda CDM predicts in ways that resolve some of the observed tensions. No replacement theory has yet achieved the level of observational confirmation that lambda CDM holds. What exists is a collection of well-developed, mathematically serious alternatives, each solving some problems while introducing others. The answer will come from data, more data, better data, from Webb and the instruments that follow it, everything traced so far connects to something deeply personal: galaxies, stars, dust, heavy metals. These are the ingredients of planets, and planets are the only place we know of where life exists. The chain from the Big Bang to a living cell runs through all of it. Hydrogen formed in the Big Bang. Stars fused that hydrogen into heavier elements. Supernovae scattered those elements into space. Dust clouds, enriched by generations of dead stars, collapsed into new solar systems. Rocky planets formed from the dust and metals in those clouds. On at least one of those planets, chemistry became complex enough to produce life. Each link in that chain takes time. The Standard Model placed the emergence of rocky planets at roughly 9 billion years after the Big Bang at the earliest. That was how long it took for enough stellar generations to produce the necessary heavy elements and distribute them widely enough for planet formation to begin at scale. Webb's findings push every link in that chain earlier. If the first galaxies formed faster than predicted, they enriched the surrounding universe with heavy elements sooner. If those early galaxies went through multiple stellar generations within the first billion years, they seeded space with the building blocks of rocky planets, hundreds of millions of years ahead of schedule. Some of the dusty galaxies from within the first billion years already contained silicon, oxygen, iron, and carbon at concentrations sufficient to build rocky bodies. The raw materials for planets were available earlier than the Standard Model placed them. The implication is significant. Life, as a possibility, may have had a head start. Somewhere in the universe, on a rocky planet forming from an early metal-rich cloud in an early massive galaxy, the chemistry of life may have had billions of extra years to develop. If life can arise anywhere in the universe, the earliest opportunity for it to do so may be billions of years earlier than scientists previously calculated. This does not mean we have found evidence of early life. We have found evidence of early conditions that could support it. The gap between those two things is vast, but it is meaningful. Every year that life has had more opportunity to develop somewhere in the cosmos is another data point in the probability calculation for whether we are alone. The universe may have been producing the conditions for life for far longer than we imagined. And the tools being built right now, on the ground and in orbit, are aimed directly at exploring that window. Webb is the most powerful observatory humanity has ever placed in space. It may not hold that title for long. Several major projects are already under construction or in advanced development, each designed to push beyond Webb's reach in specific ways. On the ground, the extremely large telescope is being built on a mountain in the Chilean desert. When it opens for observations, its mirror will be 128 feet across, the largest optical telescope ever constructed. Its light-collecting area dwarfs every existing telescope on Earth. It will be able to take direct images of nearby exoplanets and analyze their atmospheres for chemical signatures associated with biological processes. It will also be able to gather far more light from distant galaxies in a given observation time than Webb can, enabling faster spectroscopic surveys of early universe objects. Also under construction is the 30-meter telescope, planned for a high-altitude site in Hawaii. Its mirror diameter, roughly 100 feet across, gives it a combination of resolution and sensitivity that will complement Webb's infrared capabilities with detailed optical observations. In space, the Nancy Grace Roman Space Telescope is scheduled to launch in the near future. It carries a mirror similar in size to Hubble's, but equipped with a camera that can image an area of sky 100 times larger in a single exposure. Roman will conduct wide-field surveys of vast numbers of galaxies, mapping the large-scale structure of the universe with unprecedented detail. Those maps will provide the statistical power to test competing cosmological models against each other. The European Space Agency's Euclid mission, which launched in 2023, is already conducting a survey of the shape and distribution of galaxies across billions of light years. Its data is expected to provide the most precise measurement yet of the sigma-8 parameter and potentially sharpen or resolve the tension between the observed and predicted growth of cosmic structure. Further in the future, several concepts for next-generation space telescopes have been proposed to space agencies. Some are designed to detect gravitational waves from the early universe, a signal that would provide direct evidence of what happened in the moments before the cosmic microwave background was formed. Others are designed for extreme ultraviolet observations that would reveal the detailed structure of the reionization era. Each instrument contributes a piece of the answer to the questions Webb has raised. Together, they represent the largest coordinated effort to understand the deep structure of the universe in the history of astronomy. And the central question driving all of it is one that Webb itself has brought into sharp focus. 13.8 billion years is the accepted age of the universe. It is derived from the expansion rate of the universe today, the pattern of the cosmic microwave background, and the known physics of the Big Bang. It is one of the most precisely measured quantities in all of science. And a small but serious group of researchers is asking whether it might be wrong. The Hubble tension is the clearest entry point into this question. Two independent methods for measuring the expansion rate of the universe disagree. The disagreement has grown with each improved measurement. If the expansion rate that cosmologists use to calculate the age of the universe is incorrect, the age estimate changes. A higher expansion rate produces a younger universe. A lower expansion rate produces an older one. Some analyses of the early universe anomalies have suggested that a universe somewhat older than 13.8 billion years would reduce the tension between the observed properties of early galaxies and what the models predict. If the universe had more time before the Big Bang, as currently dated, the galaxies Webb found would have had more time to form, and the mass problem would become less severe. This reasoning has led a few researchers to explore cosmological models in which the universe either began slightly earlier than current measurements, placed the Big Bang, or in which the universe passed through a phase before the Big Bang, a prior epoch of some kind, whose energy eventually triggered the expansion we call the Big Bang. These are sometimes called bouncing cosmology models, in which the current expansion follows a prior contraction. The mathematical framework for some of these models is developed and serious. They are not fringe science. They are published in peer-reviewed journals and developed by credentialed researchers. They are simply speculative, meaning they await the kind of observational confirmation that would move them from possibility to theory. The direct evidence for an older universe does not yet exist. The measurements pointing that way are indirect, inferred from the anomalies, rather than measured from a direct observation of the age itself. But the question is now being asked openly in ways it was not 5 years ago. Webb has made it legitimate. The data it has returned has created enough of a gap between observation and theory that even the most fundamental parameter of our cosmic model, its age, is back on the table for examination. And underneath that question lies an even deeper one that Webb has been circling around since its first images arrived. James Webb launched with a list of goals: observe the first galaxies, study the atmospheres of distant planets, look at stars forming inside nearby nebulae, map the distribution of matter across deep space. In every one of these areas, it has exceeded expectations, and in exceeding expectations, it broke things. It broke the record for the most distant confirmed galaxy twice. It broke the predicted count of massive early galaxies, finding roughly twice as many as the models allowed. It broke the assumed timeline of cosmic dust, finding 70 dusty galaxies that could not exist as early as they were found. It broke the assumed relationship between black hole mass and galaxy mass in the early universe, showing that black holes grew faster than their host galaxies in ways the model did not predict. It broke the assumed timing of reionization, finding a galaxy clearing its surrounding hydrogen fog hundreds of millions of years ahead of schedule. It found stars with impossible age measurements. It found chemical enrichment that required stellar generations the universe had no time for. It found mass and structure and complexity packed into the first few 100 million years of cosmic history at a density that the Standard Model had never predicted. All of that in roughly 3 years of operation. Each broken expectation produced something useful. Each anomaly sharpened the questions. Each impossible measurement forced a more careful examination of the tools, the models, and the assumptions. That is exactly how science is supposed to work. But one question sits at the center of all of it, and Webb has not answered it. Where did the first mass come from? Every galaxy Webb has found in the early universe, every impossible cluster of stars, every ancient stellar population, every dusty giant from the edge of the observable cosmos. All of them require a starting point, a seed, a first overdensity of matter that gravity could grab onto, a first dark matter halo dense enough to begin pulling in gas, a first moment when the smooth, featureless fog of the post-Big Bang universe developed a lump large enough to grow into everything that followed. The Standard Model places the origin of those seeds in quantum fluctuations during inflation, microscopic ripples in the fabric of the early universe that were stretched to cosmic scales by the rapid expansion. That explanation works well enough for the large-scale structure of the modern universe. The cosmic microwave background shows exactly the kind of pattern you would expect from inflation-driven seeds. But the earliest galaxies Webb is finding are too big, too early, and too numerous to grow from those seeds in the available time, at least under standard assumptions. Either the seeds were different, or they formed by a different process, or something accelerated the growth from seed to galaxy in a way that the model does not yet contain. Webb is collecting the most important dataset in the history of observational cosmology. Every image is a data point, every spectrum is a clue, every record broken is an arrow pointing toward the answer. The answer is not here yet. The universe is older than we thought, stranger than we imagined, and busier in its earliest moments than our best theory ever allowed. And every time we build a better eye to look at it, it shows us something we did not expect.